Hey, Dr. B here, and let's take a look at chemical bonds and forces. Let's start with the strongest and work our way down to the weakest. The strongest chemical bonds are networked. For example, diamond can come in at up to 5,000 kilojoules per mole for those bonds. If you have an ionic bond, that's an electrostatic attraction between a positive and a negative ion. For example, sodium chloride, a little bit weaker. You can also have metallic bonds, which can be surprisingly strong. The iron-to-iron bond can be 100 to 500 kilojoules per mole. In all three of these cases, you don't see individual molecules. It's a network or a lattice. If you have an intramolecular bond, that means you have individual molecules, and that means you have a covalent bond. For example, a carbon-carbon bond. And now we're getting down to as little as 150 kilojoules per mole, but notice the overlap here. There's quite a bit of overlap. And if you have individual molecules, you're going to have intermolecular forces between them. Notice we're using the term forces rather than bonds. People start to draw dotted lines rather than solid lines so you can see where the individual molecules are. The strongest is an ion dipole force, for example, a sodium cation attracted to water. Very positive there, very negative there. Hydrogen bond force is a special type of dipole force. The electrons are unevenly shared, pretty extremely so. So if you have fluorine, oxygen, or nitrogen that's attracted to a hydrogen, all three of those are very electronegative, rendering that hydrogen particularly positive. And it will be attracted strongly to a lone pair. We call that a hydrogen bond. And this can be example in water, up to 200 kilojoules per mole. We get much weaker when you simply have the attraction from the unevenly shared electrons in a molecule. For example, carbon monoxide. That oxygen is electronegative, the carbon is electropositive, therefore there's a slight plus to minus attraction there, but we're getting into single digits for kilojoules per mole. And a freebie that's present in all molecules and substances is a London dispersion force, where there might be a temporary dipole that can form for just about anything. Even two nitrogen molecules would have an attraction of that variety, a dispersion force, and that's can be as little as, fractions of a kilojoule per mole. So that's an entire continuum from the very strong networked substances right down to the noble gases. Let's look at some scenarios. If you have an ionic bond and it breaks, but it doesn't form new bonds, that just must mean that that ionic substance was dissolved, because that's what happens. It breaks that ionic bond. If it's in solution, but then the ionic bond reforms, the opposite must be occurring. The substance has precipitated. If you've got no intermolecular forces or bonds at all, well, I guess you must be a gas, and if you're being specific, perhaps a noble gas. If you have intermolecular forces that are fixed, and in fact there might not be a differentiation between the intermolecular forces and the actual bonds, you're dealing with a solid. If they are fluid, it's a liquid. And consider HF. It's got a boiling point of 19 degrees Celsius. It's almost a liquid at room temperature, but HCl is a gas, even when it's quite cold. Why is that? Well, those intermolecular forces are stronger for HF, and so it can easily be in the liquid state. It requires more energy, a higher temperature, to break those intermolecular forces. That's because HF can form hydrogen bond forces. The strongest possible intermolecular force in nitrogen is only a London dispersion force. It's also true for carbon dioxide only because it's a nonpolar molecule overall. Water, on the other hand, can form a hydrogen bond force, as can HF. Methanol, also yes. Chloroform, also yes. Dipole in this case. This can form a hydrogen bond force. Chloroform cannot. I do not see F, O, or N present, so the strongest intermolecular force is a dipole-dipole. Okay. Here's a bunch of substances that are arranged by melting point. See if you can identify the strongest intermolecular force or bond that is present. Let's begin with a diamond. Melting point can be as much as 5,000 degrees Celsius. Here we have a networked covalent bond between them. Incredibly strong. Iron, the strongest bond must be metallic. Iron oxide, I see ionic bonds there. As for table salt, similarly, ionic bonds. Continuous lattice of them. Quartz also has a continuous lattice, but in this case there's no metal present. Almost, I mean, we have a metalloid. So we would call that a network covalent bond. Here's an interesting one. It's just a lump of sulfur, and yet the melting point is 239. Sulfur, that's just S8. Every single one of those atoms has equal desire for electrons. It's purely covalent, being to the right of the staircase, so we can't do any better than a London dispersion force, and yet, look at that high melting point. I think it's just that you have so many per molecule that it brings it up. Lump of sodium, you might say ionic, but no. These are just sodium atoms. And they have an equal desire for electrons. Don't forget they're metals, so we have a metallic bond present. Water has the covalent bonds between the molecules and covalent bonds within the molecules, and hydrogen forces between the molecules. Ethanol can form a hydrogen bond force. And by the way, we're not asking what's the strongest bond that's present, but what are the strongest bonds or forces that must be broken in order to melt it, right? So you must be dealing with the hydrogen bond force in order to melt it. If we break the hydrogen to oxygen bond in water, that's a chemical reaction. Similarly, we have to break that hydrogen bond in order to melt ethanol. Propane is just a hydrocarbon, C3H8. So remember, carbon to hydrogen is an exception. Those are nonpolar covalent bonds. You can't do any better than London dispersion forces. Same thing for methane, and there's fewer per molecule, giving it an even lower melting point, making it even easier for it to enter the gaseous state. And those are also London dispersion forces. This is an overview of chemical bonds and forces.